Night falls early over Berlin in the winter of 1900, and in a cramped office at the University of Berlin, a 50-something physicist with stern features and immaculate manners sits hunched over sheets of paper that refuse to yield, while outside the gas lamps flicker against the fog and the carriages rattle on cobblestones that have survived more than one revolution. Max Planck is not in the habit of making revolutions. He admires order, reveres classical harmony, and in the neat lines of his notebooks there is no hint that within a few hours he will take a step that will crack open the comfortable universe of 19th century physics and lead, by a sequence of unlikely episodes, to the strange territory now called quantum physics. He is only trying to fix a problem about the colour of light from hot objects, and behind that modest intention lies a century of accumulated confidence, of equations and forces and fields that seem to have tamed nature into a comprehensible mechanism. To understand why Planck's tremor of pen on paper that night matters, you have to picture the world of physics as it then stands. A world born in the imagination of men like Isaac Newton, who 2 centuries earlier had looked at the falling apple and the circling moon and decided that the same mathematical law governs both, writing down a formula that could predict the paths of planets and cannonballs with equal ease, and with it installing the idea that the universe is a grand clockwork. In Newton's cosmos, if you tell him where every particle is and how fast it's moving, his laws of motion and gravitation will tell you, at least in principle, what will happen next, and what happened before, all the way back to the beginning. Uncertainties are merely a matter of human ignorance, not a feature of reality. That clockwork view is embellished through the 18th century by the language of differential equations, by the formalism of Lagrange and Hamilton, by Laplace, who famously imagines an intelligence that, knowing all positions and velocities, could read the future like a book. When, in the early 19th century, light itself is brought into the fold, first as mysterious rays obeying geometric rules, then as waves undulating through an all-pervasive ether, the picture only seems to grow more unified. Michael Faraday, with his wild hair and unshakable experimental instinct, draws lines of force around magnets and coils of wire, insisting that these invisible structures are as real as any billiard ball. James Clerk Maxwell, armed with prodigious mathematical talent and a poet's fascination with abstraction, writes down 4 equations that look almost innocent and yet encode a new synthesis, declaring electricity, magnetism and light to be aspects of a single electromagnetic field filling space. In the elegant curves of Maxwell's theory, light waves propagate at a fixed speed, determined by the electric and magnetic constants of the vacuum itself. No matter how you move, the equations seem to whisper that speed does not change. It is a quiet scandal lodged inside an otherwise triumphant edifice, and by the time Planck sits in Berlin wrestling with heat radiation, another patent clerk in Bern is about to tear at that particular thread and unravel space and time. But Einstein's relativity lies a few years ahead. For now, the tension that gnaws at the late Victorian physicist is not the relativity of time, but the stubborn misbehaviour of energy at the microscopic scale. Heat, long a topic of fascination, has been reinterpreted as the motion of atoms and molecules, courtesy of statistical mechanics developed by figures like Boltzmann and Gibbs, who argue that temperature is not a kind of fluid, as in older caloric theories, but a measure of average kinetic energy. In their hands, probabilities invade physics not as a deep principle, but as a practical necessity. You cannot track every molecule in a gas, so you treat them as a statistical crowd and derive laws about pressure and temperature that hold on average. Ludwig Boltzmann, in particular, stakes his reputation on the reality of atoms, despite vocal skeptics who prefer to see them as mere convenient fictions, and on the idea that entropy is a measure of how many microscopic configurations correspond to a macroscopic state, engraving his famous relation S scans K log W on his tombstone years before he dies in despair. For such men, randomness is an epistemic crutch. The underlying motion of particles remains perfectly deterministic. The late 19th century believes that, aside from a few clouds on the horizon, anomalies in the orbit of Mercury, the dark mystery of the ether, and an awkward puzzle about blackbody radiation, physics is essentially complete. Blackbody radiation sounds esoteric, but it is the colour and intensity of glow that any object emits when heated, and it turns up everywhere from furnace walls to stars. Experimentalists in Berlin and elsewhere build vaulted cavities with tiny openings, heating them until they glow with a smooth, featureless spectrum, a kind of idealized light that depends only on temperature, not material. As they measure the energy emitted at different wavelengths with increasing precision, they notice that at low frequencies, classical theories can more or less cope, but at higher frequencies, in the ultraviolet, the standard equations predict a catastrophe. The energy should grow without bound. The furnace should pour out infinite power at short wavelengths, a conclusion so absurd it earns the moniker ultraviolet catastrophe. Classical equiartition, the idea that energy is shared equally among all possible modes of vibration, seems to doom the theory. For a man like Planck, trained in the austere rigour of German science and personally inclined toward conservatism, this is not a call to revolution, but an invitation to find a clever mathematical trick. In the cramped corridors of the Physikalische Technische Reichsanstalt, an institution designed to bring precision to measurements and standards, Planck has access to the latest data, carefully calibrated curves of intensity versus wavelength at various temperatures. He tries to fit them with formulas inspired by classical electromagnetism and thermodynamics, tinkering with constants, exploring asymptotic behaviours, searching for a bridge between heuristic rules proposed by predecessors like Wien and Rayleigh-Jeans. In October 1900, he finds an interpolation formula that matches the experiments alarmingly well, but it lies uneasy on his sense of physical meaning. Still, on October 19th, he presents it to the German Physical Society, a pragmatic result that elicits polite approval without fanfare. What gnaws at him afterward is not the applause, but the lack of derivation from first principles. He is determined to endow his formula with a theoretical pedigree, and for that he turns, reluctantly, toward Boltzmann's statistical ideas, which he had long resisted as overly probabilistic and philosophically distasteful. Sitting at his desk in November, Planck treats the walls of the furnace as a collection of tiny oscillators, resonant charges that can absorb and emit electromagnetic energy, and he asks how the energy is distributed among them. To recover his empirical formula, he realizes he must abandon the classical picture of continuous energy, and instead imagine that each oscillator can only possess energy in discrete parcels, proportional to its frequency, E Schwarzschild, where n is an integer, n is the frequency, and h is a constant that at first looks like a mere fitting parameter. This chopping of energy into quanta is an act Planck later describes as an act of desperation, a mathematical trick to make Boltzmann's counting work out and give the right curve. On December 14th, 1900, at a meeting whose date future generations will mythologize as the birth of quantum theory, he presents a derivation of his law using this new hypothesis, but neither he nor his audience fully grasp the profundity of what has just happened. They see it as a technical maneuver, not a declaration that nature at a fundamental level might be granular rather than smooth. While Planck tinkers with quanta in Berlin, elsewhere the notion that atoms are real, discrete building blocks of matter is still under debate, with some, like the chemist Ostwald, preferring to treat them as abstract entities. Yet across Europe, fragments of evidence accumulate. Brownian motion, the jittery dance of pollen grains in water observed decades earlier by Robert Brown, is revisited by physicists like Jean Perrin, who will soon use it to estimate Avogadro's number and give tangible weight to the atomic hypothesis. In laboratories in Leiden, Kamerlingh honours cool substances to temperatures unimaginably low, skating near absolute zero, discovering superconductivity in mercury in 1911 when electrical resistance vanishes abruptly, a phenomenon that classical electrodynamics cannot explain, and that will later become a playground for quantum thinking. The stage is crowded with discrepancies, puzzles, experimental whispers that the seemingly continuous fields and smooth energy distributions beloved of Victorian theorists may not be the final word. Into this ferment steps a young man working at the Swiss Patent Office in Bern, a job that leaves his mornings and evenings free for thought. Albert Einstein in 1905 is not yet the icon of wild hair and gentle smile. He's an outsider who has failed to secure an academic post, whose professors thought him too rebellious, but his mind is fixed on the foundations of physics, especially on light and motion. One of the clouds on the 19th century horizon is the failure to measure the motion of the Earth through the ether. The Michelson-Morley experiment of 1887 found no shift in interference fringes as the apparatus rotated, implying that the speed of light is the same in all directions, contrary to the simple idea of an ether wind. Lorentz and Fitzgerald proposed that objects physically contract in the direction of motion to account for this, but their transformations remained clumsy patches. Einstein, staring at the railway clocks and synchronized signals that regulate Swiss trains, decides to take the constancy of the speed of light as a principle and let space and time themselves become flexible, leading to special relativity with its time dilation, length contraction, and merging of space and time into space-time, where Maxwell's equations make natural sense. Yet in the same miracle year, 1905, Einstein writes a less famous but equally revolutionary paper that reaches back to Planck's desperate hypothesis and pushes it further. Experimentalists studying the photoelectric effect have found that light shining on a metal surface can eject electrons, but with peculiar properties. There is a threshold frequency below which no electrons emerge, no matter how intense the light, and the kinetic energy of the ejected electrons depends on the light's frequency, not its brightness. In classical wave theory, energy is spread uniformly over the wavefront, and a sufficiently intense beam, regardless of colour, should eventually knock electrons out by cumulative effects, but this is not what nature does. Einstein suggests that light itself consists of discrete packets of energy, quanta later dubbed photons, each with energy E gen, directly inheriting Planck's formula, but now applied to the radiation field, not just to oscillators in a furnace wall. When a photon strikes an electron, it transfers its energy in a single transaction. If that energy is above a certain binding energy for the metal, the electron escapes with kinetic energy equal to Hn minus the work function, explaining the threshold and the linear dependence. To the conservative Planck, who had hoped his energy quanta were merely a calculational device, Einstein's hypothesis is alarming because it seems to break the beautiful continuity of Maxwell's waves and resurrects corpuscles of light, entities Newton would have recognized. The wider community largely ignores or resists the idea. Einstein himself will later be awarded the Nobel Prize not for relativity, but explicitly for his work on the photoelectric effect. Yet at the time, many see his light quanta as a step backward. Still, over the next decade, piece by piece, the quantum seed grows. In 1907, Einstein applies the notion of quantized energy to the vibrations of atoms in a solid, offering an explanation for the specific heat of solids that drops at low temperatures, another phenomenon that classical physics mispredicts. Around the same time in Manchester, Ernest Rutherford, analysing the scattering of alpha particles by thin gold foil, discovers that atoms are mostly empty space with a tiny massive nucleus at the centre, a solar system in miniature, overturning the plum pudding model of J.J. Thomson, and setting the stage for a new question. How do electrons orbit this nucleus without radiating away their energy, as Maxwell's equations insist accelerated charges must do? By 1911, as the Solvay Conference gathers the leading minds of physics in Brussels, under the watchful patronage of industrialist Ernest Solvay, the atmosphere is a mixture of admiration for the achievements of the past and growing unease about these quantum oddities. There, amidst cigar smoke and heavy curtains, Planck, Lorentz, Poincaré, Einstein and others debate the implications of quanta, but the language is still halting, the ideas embryonic. The next step comes from a quiet young Dane with a deep sense of philosophical subtlety and a habit of long, meandering conversations punctuated by awkward silences. Niels Bohr. Bohr travels to Manchester to work with Rutherford. Absorbing the nuclear picture of the atom, then returns to Copenhagen determined to find a model that reconciles classical orbits with Planck's quantization, perhaps only as a halfway house to a deeper theory. In his 1913 trilogy of papers on the constitution of atoms and molecules, Bohr proposes that electrons inhabit certain allowed circular orbits around the nucleus, where their angular momentum is quantized in units of h2p, later denoted h. In these stationary states, they do not radiate. Radiation occurs only when an electron jumps between such levels, emitting or absorbing a quantum of light whose frequency matches the energy difference divided by h. On the face of it, Bohr's model flagrantly violates classical mechanics, imposing quantization by fiat and treating electron orbits as both well-defined and magically immune to radiation. Yet the payoff is staggering. His formulae reproduce the spectral lines of hydrogen with unprecedented accuracy, explaining the Balmer series and predicting others. For the first time, the strange patterns of light emitted by atoms, catalogued painstakingly for decades by spectroscopists, acquire a theoretical footing, and Bohr's success forces his contemporaries to take quantization seriously, even if the underlying mechanism remains mysterious. As the First World War engulfs Europe, scattering scientists to military projects and shattering old empires, quantum ideas bide their time in notebooks and small seminars. In Göttingen, a town that has become a capital of mathematics, the likes of Hilbert, Klein, and later born Foster, a culture of rigorous abstraction, while in Munich Arnold Sommerfeld refines Bohr's model, adding elliptical orbits, relativistic corrections, and quantum numbers that organise spectral lines into finer structures. Sommerfeld's school trains a generation. Pauli, Heisenberg, and others pick up both technical skill and an appetite for foundational clarity. At the same time, in Leiden, Lorentz retires amid hails of admiration, while his former student Ehrenfest broods over statistical mechanics and the meaning of quanta, holding informal colloquia where the world's leading physicists drop in to argue. Outwardly, classical physics still dominates textbooks. Inwardly, pressure is building, like a superheated liquid awaiting nucleation. By the early 1920s, the list of phenomena resisting classical interpretation has grown unwieldy. Atomic spectra with fine and hyperfine structure, the anomalous Zeeman effect where splitting of spectral lines in magnetic fields refuses to match simple predictions, the stability of atoms against collapse, the peculiar behaviour of electrons in metals and insulators, and the rules of chemical bonding that chemists have catalogued empirically. Louis de Broglie, a French prince by birth and physicist by inclination, proposes in his 1924 thesis a bold unification. If light, once the paradigmatic wave, exhibits particle-like quanta, perhaps matter, long treated as particulate, possesses wave-like properties. To each particle of momentum p, he assigns a wavelength, SDL, hp. In this picture, an electron in Bohr's orbit wraps around the nucleus like a standing wave, fitting an integer number of wavelengths along the circumference, thus producing quantized angular momentum as a mere resonance condition. A whisper that the deep theory might be fundamentally wave-like rather than mechanical. While de Broglie speculates, another drama unfolds in Copenhagen and Göttingen, where Werner Heisenberg, a young man plagued by hay fever and uninterested in visualizing electron orbits, stands on the windswept island of Helgoland in the North Sea in 1925, seeking relief for his allergies and escape from the interpretive muddle of old quantum theory. He decides to focus only on observable quantities, like the frequencies and intensities of spectral lines, discarding any picture of electron paths inside the atom as metaphysical excess. In working out the algebra of these observables, he finds that the quantities must be multiplied in a non-commutative way. The order of multiplication matters, unlike in ordinary arithmetic. Back in Göttingen, Max Born and Pascal Jordan recognized that Heisenberg's strange tables of numbers are matrices, objects well known in pure mathematics but now appearing at the heart of physics. Together they formalize what becomes matrix mechanics, a quantum theory where physical quantities are represented by matrices acting on abstract state vectors, and where the commutation relation between position and momentum operators, x, p, soc, encodes the impossibility of jointly assigning precise values to both. Almost simultaneously, in Zurich, an Austrian physicist with a taste for mountaintops and an intense, restless intellect struggles with quantum riddles from a different angle. Erwin Schrödinger, inspired by de Broglie's matter waves and guided by mathematical analogies with optics and Hamilton-Jacobi theory, writes down in late 1925 a differential equation for a wave function, psin, a complex valued function spread over space whose evolution in time is governed by a linear operator corresponding to the Hamiltonian, the energy of the system. When he applies this equation to the hydrogen atom, he recovers Bohr's energy levels and the spectral lines, but with continuous smooth wave patterns instead of jumpy orbits. Schrödinger presents his wave mechanics as a more intuitive, visually and mathematically tractable alternative to Heisenberg's matrix jungle, and for a brief period he believes he has restored continuity to physics, imagining electrons as smeared-out charge clouds described by Pep, with no need for mysterious quantum jumps. The apparent conflict between matrix mechanics and wave mechanics sparks debates and competing schools, but within months a deeper unification emerges. Schrödinger demonstrates that his wave mechanics is mathematically equivalent to the matrix approach, merely a different representation of the same underlying structure. The quantum state of a system can be represented either as a vector in an abstract Hilbert space, as a wave function in coordinate space, or as a matrix of transition amplitudes. The physics lies not in any particular picture, but in the algebra of operators and the probabilities they generate. Born, reflecting on the role of the wave function, makes a leap that will shape all subsequent thinking. He proposes that C sus2 gives not charge density, or a smeared-out electron, but a probability density, the likelihood of finding a particle in a given region upon measurement. With this statistical interpretation, quantum mechanics acquires its distinctive probabilistic core, no longer a veneer over deterministic motion, but a fundamental feature. Heisenberg, soon after, articulates his uncertainty principle, not as a statement about measurement sloppiness, but as a structural fact. Position and momentum operators do not commute, leading to the inequality dx dp rostjust h2, which bounds the product of their dispersions in any state. An electron cannot possess an arbitrarily precise position and momentum simultaneously. The very notion of a trajectory, a sequence of exact positions at exact times, becomes suspect. Bohr, now the elder statesman of the Copenhagen group, weaves these results into a philosophical framework he calls complementarity, arguing that quantum phenomena require mutually exclusive classical concepts, wave and particle for example, that cannot be applied simultaneously, but together provide a full account of experiments. His language is notoriously opaque, blending Kantian echoes with labyrinthine sentences, yet his influence on how physicists talk and think about quantum theory is immense, especially through endless discussions, often stretching far into the night, with visitors who leave both illuminated and exhausted. Around this embryonic formalism, experiments continue to shape intuition. In 1927, at Bell Labs in New Jersey, Clinton Davison and Lester Germer fire electrons at a nickel crystal and observe a diffraction pattern, exactly as de Broglie's waves predict, thereby giving direct empirical support to matter waves and the wave function. A few years earlier, in 1922, the Stern-Gerlach experiment in Frankfurt has already revealed a new quantum property. Otto Stern and Walter Gerlach send a beam of silver atoms through a non-uniform magnetic field and expect a continuous spread of deflections according to classical magnetic moment orientations, but instead the beam splits into two discrete spots, indicating that the atomic magnetic moment is quantized in two orientations. This is the first clear sign of what will soon be called spin, an intrinsic angular momentum not attributable to any simple spinning of a charged sphere, but an inherent quantum degree of freedom, later understood as rooted in the representation theory of the rotation group and in the Dirac equation. Wolfgang Pauli, sharp-tongued and uncompromising in his criticism, formulates in 1925 the exclusion principle. No two electrons in an atom can occupy the same quantum state, an empirical rule that organizes the periodic table and explains chemical violence. In the abstract language of quantum mechanics, this becomes the antisymmetry of the wave function for fermions, particles with half-integer spin under exchange, leading to Fermi-Dirac statistics, while integer spin particles, bosons, exhibit symmetric wave functions and obey Bose-Einstein statistics, grouping together in shared states rather than keeping their distance. Satindra Nath Bose, in Kolkata, first derives Planck's law by treating photons as indistinguishable particles with an unusual counting method, and Einstein, recognizing the generality, extends the idea to atoms, predicting Bose-Einstein condensation, a peculiar state of matter at low temperatures where a macroscopic fraction of bosons collapse into a single quantum state, a prediction that will take 7 decades to realize experimentally. Amid these developments, in the late 1920s, a slender, taciturn Englishman with a gift for austere beauty in equations enters the scene. Paul Dirac, working in Cambridge, seeks a quantum mechanical equation for the electron that respects special relativity, whose structure links space and time into spacetime and demands that energy and momentum transform in 4 vectors. Schrödinger's equation is not relativistically invariant. Klein and Gordon have tried a relativistic wave equation, but encountered negative probabilities. Dirac constructs a linear first-order equation in both time and space derivatives, involving matrices now called gamma matrices, and finds a description that naturally incorporates spin 1 to 2 and predicts a new phenomenon. For consistency, the energy spectrum includes negative energy solutions. At first, these seem unphysical, but Dirac interprets them as a sea of filled states, with holes corresponding to antiparticles, and when the positron is discovered in cosmic ray experiments by Carl Anderson in 1932, Dirac's vision is vindicated, signalling that quantum theory married to relativity inevitably brings particle-antiparticle symmetry. While theorists build these abstract structures, the experimental theatre widens from atoms to nuclei and cosmic rays. In 1932, James Chadwick discovers the neutron, a neutral nuclear constituent that explains isotopes and opens new questions about nuclear forces. Fermi, Pauli, and others puzzle over beta decay, where electrons are emitted from nuclei with a continuous energy spectrum rather than discrete lines, violating energy conservation if only the electron and nucleus are considered. Pauli in 1930 somewhat apologetically proposes a new, light-neutral particle, the neutron before Chadwick claims that name, later renamed the neutrino by Fermi, who constructs a theory of beta decay treating it as an interaction among 4 fermions at a point, one of the first quantum field theories for weak processes. The notion that particles are excitations of underlying fields begins to take firmer hold. Even as early quantum electrodynamics, the quantum field theory of light and charged particles grapples with infinities in self-energy and radiative corrections that threaten to render predictions meaningless. The 1930s and 1940s see quantum mechanics extended into chemistry and solid-state physics, giving microscopic explanations for chemical bonding, band structures in crystals, electrical conductivity, magnetism, and the peculiar behavior of semiconductors that will one day underpin the transistor and, by extension, the entire digital world. Linus Pauling applies quantum valence bond ideas to molecules, explaining directional bonds and resonance in benzene, while Bloch works out the wave functions of electrons in periodic lattices, showing how energy bands and band gaps arise naturally from quantum motion in a periodic potential. Heisenberg, in a very different domain, proposes a quantum model for ferromagnetism based on spin-spin interactions, presaging the rich interplay between quantum optics and condensed matter that will dominate later decades. Yet the looming storm clouds of war pull physicists into new arenas, especially nuclear fission, discovered in 1938 by Hahn, Strassmann, and Meitner, which unleashes enormous energy from splitting heavy nuclei and swiftly becomes the focus of successive secret projects. In the Manhattan Project, quantum physics, born as a subtle revision to blackbody radiation formulas, now directs metallurgical, chemical, and engineering work on an unprecedented scale, as theorists like Fermi, Bethe, and Teller, alongside experimentalists and engineers, apply quantum nuclear models to chain reactions, neutron moderation, and critical masses. Quantum mechanics is not the only ingredient in atomic bomb design, but without the understanding of nuclear binding energies, neutron cross-sections, and the shell structure of nuclei, the enterprise would be blind. At Los Alamos, Oppenheimer presides over a convocation of the world's leading minds, many refugees from European turmoil, and in the desert of New Mexico, the first nuclear explosion marks not only a geopolitical turning point, but a sobering demonstration of how deeply quantum ideas have penetrated, from discrete nuclear levels to macroscopic annihilation. After the war, some of these same figures pivot to more esoteric questions, among them the urgent need to tame the infinities in quantum electrodynamics that had been set aside during wartime pragmatism. The post-war years bring a sharpened focus on quantum field theory, the framework in which particles are quanta of fields that pervade space, with creation and annihilation, operators replacing fixed numbers of particles. In the late 1940s, Hans Bethe, on a train back from a conference, performs the first non-relativistic renormalization calculation of the Lamb shift, a tiny difference in energy between 2 hydrogen levels that Dirac's original theory predicts to be degenerate. Experimentalists Willis Lamb and Robert Rutherford have measured this shift using microwave techniques, observing a discrepancy that cries out for explanation. Julian Schwinger in the United States, Shinichiro Tomonaga in Japan, and a young American with a knack for cartoonish diagrams, Richard Feynman, develop different but equivalent formulations of quantum electrodynamics, QED, that systematically absorb the troublesome infinities into redefined masses and charges. This renormalization program, though philosophically unsettling to some, produces astonishingly accurate predictions, such as the anomalous magnetic moment of the electron, measured and computed to many decimal places, establishing QED as one of the most precise and successful theories in science. Feynman's path integral formulation, which represents the quantum amplitude for a particle to go from one point to another as a sum over all possible paths, each weighted by an exponential of the classical action, introduces a deeply non-classical viewpoint. Instead of a single trajectory, every conceivable history contributes, interfering constructively or destructively, and the classical path emerges only as a stationary phase approximation when actions are large compared to h. This idea generalizes naturally to fields, where Feynman diagrams become bookkeeping devices for perturbation expansions, depicting interactions as particle lines that split and join, at vertices corresponding to fundamental couplings. Though originally pragmatic, these diagrams soon become a visual language through which entire generations of physicists think about quantum processes, from electron-positron annihilation to vacuum polarization, where temporary virtual particle pairs flicker in and out of existence, modifying forces at short distances. As quantum field theory matures, the strange world of quantum phenomena broadens beyond the microscopic collisions in accelerators into macroscopic quantum states. In 1957, in the chilly laboratories of Leiden and elsewhere, theorists Bardeen, Cooper and Schrieffer construct a theory of superconductivity, showing that electrons in a metal can form bound pairs, Cooper pairs, through effective attraction mediated by lattice vibrations, and that these pairs condense into a coherent quantum state described by a single macroscopic wave function. This explains zero resistance and the Meissner effect, where magnetic fields are expelled from superconductors as a consequence of phase coherence over enormous numbers of particles. In such systems, quantum phase, a subtle quantity in single particle wave functions, becomes macroscopically rigid, giving rise to quantized flux vortices and Josephson junctions, where supercurrents tunnel between superconductors across thin insulating barriers, oscillating at frequencies directly proportional to voltage, enabling extraordinarily precise measurements of fundamental constants. Another family of macroscopic quantum effects appears in two-dimensional electron systems in strong magnetic fields and low temperatures, culminating in the discovery of the integer and fractional quantum Hall effects. In 1980, Klaus von Klitzing measures the Hall conductance, the transverse conductivity in a current-carrying conductor under magnetic field, and finds that it is quantized in integer multiples of e Phi with staggering precision, insensitive to impurities or material details. This suggests that the conductance is a topological invariant, a global property of the system's quantum state, tied to the topology of filled Landau levels. A few years later, Tsui, Stormer and Gossard discover the fractional quantum Hall effect, where conductance plateaus occur at fractional values like 1 to 3, indicating the emergence of new quasi-particles with fractional electric charge and exotic statistics, any ones that interpolate between bosons and fermions in 2 dimensions. These phenomena reveal that quantum mechanics, combined with many body interactions and topology, can produce states of matter whose excitations do not fit the simple particle paradigms of earlier decades. Even as condensed matter exposes new quantum phases, particle physics uses quantum field theories to build a standard model of fundamental interactions. In the 1960s and 1970s, through the work of Glashow, Weinberg, Salam, de Hooft and many others, non-abelian gauge theories and the mechanism of spontaneous symmetry breaking are harnessed to unify electromagnetic and weak interactions into an electro-weak theory, while quantum chromodynamics, QCD, emerges as the theory of the strong force, with quarks carrying color charge bound by gluons into hadrons. The phenomenon of asymptotic freedom, discovered by Gross, Wilczek and Politzer, shows that in QCD, the coupling becomes weaker at high energies, explaining why quarks at short distances behave almost freely, while at long distances they are confined. The standard model as a quantum gauge field theory rests entirely on quantum principles. Particles are excitations of fields, interactions mediated by gauge bosons, vacuum expectation values of fields give masses to particles via the Higgs mechanism, and the vacuum itself seethes with fluctuating fields and virtual processes. To probe and confirm this invisible architecture, giant accelerators like CERN's Large Hadron Collider hurl particles together at immense energies, their collisions producing showers of secondary particles that detectors record as patterns of tracks and energy deposits. In 2012, the discovery of a boson with properties matching the long-predicted Higgs particle crowns this effort, giving mass to the W and Z bosons that mediate weak interactions and validating the mechanism of electroweak symmetry breaking. Yet even as the standard model triumphs, it leaves deep questions unresolved. The nature of dark matter and dark energy inferred from cosmological observations, the pattern of particle masses and mixings, the apparent fine-tuning of certain parameters, and the incorporation of gravity, which remains described by Einstein's general relativity, a classical geometrical theory of space-time curvature, not yet reconciled fully with quantum principles. Amid this grand edifice, the conceptual strangeness of quantum theory, present since Planck's night and sharpened by Bohr and Heisenberg, continues to provoke unease, nowhere more so than in something as simple yet baffling as the double-slit experiment. When electrons or photons are fired one by one at a barrier with two narrow slits, and a screen behind it records their arrival, the pattern that accumulates over time exhibits interference fringes, characteristic of waves passing through both slits and interfering. Yet each detection is localized, a single dot on the screen. If detectors are placed at the slits to determine which path each particle takes, the interference pattern disappears, replaced by two single-slit patterns, as if the particles now behave like classical corpuscles that choose one route. It is as though the very possibility of knowing the path erases the interference, as though nature is sensitive not only to what is but to what can be known, and the wave function, evolving smoothly via Schrödinger's equation, seems to undergo an abrupt non-unitary collapse upon measurement, projecting onto one outcome with probabilities given by Sapburst-2. Einstein, who helped launch the quantum revolution with light quanta, and whose photon gas work laid groundwork for Bose-Einstein statistics, grows increasingly uncomfortable with this indeterminacy and the apparent role of observers. He engages in a long series of debates with Bohr, especially at Solvay conferences, proposing thought experiments designed to expose inconsistencies in the Copenhagen view, a photon box whose mass change might reveal the energy of an emitted photon with arbitrary precision, or diaphragms that could in principle measure which slit a particle passed through without destroying interference. Bohr parries each challenge, invoking uncertainty relations and the holistic nature of measurement setups, and for many contemporaries, his rhetorical victories reinforce the Copenhagen interpretation as the de facto orthodoxy. Yet Einstein's most enduring challenge arrives in 1935 in a paper with Podolsky and Rosen, which examines entangled states of two particles and questions whether quantum mechanics can be complete. In the EPR argument, two particles are prepared in a correlated state such that their total momentum and relative position are well defined. Measuring the position of one immediately determines the position of the other, and similarly for momentum. If quantum mechanics description is complete, then before measurement neither particle has definite values. Yet a measurement on one seems to instantaneously assign a value to the other, no matter how far apart they are. Einstein calls this spukhaft Fernwirkung, spooky action at a distance, and suggests that perhaps quantum mechanics is incomplete, lacking hidden variables that would restore locality and determinism. Bohr responds with dense philosophical prose emphasizing the indivisibility of quantum phenomena and the contextual nature of properties. But the argument remains abstract until, in 1964, John Bell derives a concrete inequality, Bell's inequality, that any local hidden variable theory must satisfy but that quantum correlations can violate. For decades, Bell's work is seen as a niche foundational contribution, but by the late 1970s and early 1980s, experimentalists like Alain Aspect in France design ingenious experiments with entangled photons, measuring correlations of their polarizations under varying settings chosen rapidly enough to close certain loopholes. The observed violations of Bell inequalities confirm that no theory based on local hidden variables can reproduce quantum predictions. The world is either non-local in some subtle sense or requires abandoning classical intuitions about realism. This does not permit faster-than-light signaling, as the statistical structure of measurement outcomes prevents harnessing entanglement for communication, but it does mean that the quantum state of a composite system cannot be decomposed into independent states of its parts with pre-existing properties. Entanglement emerges as a physical resource, not merely a philosophical curiosity, and in time it will become central to quantum information theory and technologies such as quantum cryptography and quantum computation. As these foundational issues sharpen, alternative interpretations of quantum mechanics proliferate, each trying to account for the peculiarities of measurement, probability, and reality without altering the theory's successful predictions. In 1952, David Bohm revives and extends a pilot wave theory originally sketched by de Broglie, in which particles have definite positions and are guided by a quantum potential derived from the wave function, which evolves according to Schrödinger's equation. This deterministic hidden variable theory reproduces the statistical outcomes of standard quantum mechanics, but at the price of explicit non-locality. The quantum potential depends on the configuration of all particles at once, regardless of distance. Meanwhile, Hugh Everett III, a young physicist at Princeton in the 1950s, proposes a radically different view. The universal wave function never collapses. All possible outcomes of quantum measurements are realized in a vast branching multiverse, and what we experience as randomness is a matter of self-location in one of the branches. This relative state or many worlds interpretation dispenses with special roles for observers or measurements, but raises deep questions about probability and the status of the branching worlds. Other approaches emphasize information and epistemology. In cubism, for instance, quantum probabilities are seen as personal degrees of belief of an agent, updated via experience. The wave function is not an objective physical entity, but a tool for organizing expectations, and the notorious collapse is simply Bayesian updating upon new data. Elsewhere, objective collapse models like Girardi-Rimini-Weber modify Schrödinger's equation by adding spontaneous random collapses that occur rarely for a single particle, but effectively for macroscopic superpositions, thus explaining why we do not see cats that are both alive and dead. Each of these interpretations and modifications attempts to reconcile quantum formalism with some preferred set of intuitions: locality, realism, unitarity, or classical logic. None alters the laboratory outcomes we can currently test, but they shape how researchers think about extensions of quantum theory, particularly into realms involving gravity and cosmology. Entanglement and superposition, once regarded as philosophical oddities, gradually evolve into operational tools in what becomes known as quantum information science. In the early 1980s, Feynman points out that simulating quantum systems on classical computers appears to require resources that grow exponentially with system size, because the dimension of Hilbert space grows exponentially with the number of particles. He suggests that a computer built from quantum bits, qubits, that themselves obey quantum laws might efficiently simulate other quantum systems. A qubit, unlike a classical bit that is either 0 or 1, can be in a superposition apobored, with complex amplitude satisfying 2 2. 1. Collections of qubits can be entangled, creating joint states that cannot be factorized into product states of individual qubits, and algorithms can exploit interference of amplitudes to enhance desired outcomes while cancelling others. In 1985, David Deutsch, at Oxford, formalizes the notion of a universal quantum computer, defining quantum circuits built from gates acting on qubits, and shows that such a machine could perform any computation that a classical Turing machine can, and more. For years, quantum computing remains a mostly theoretical playground, with toy algorithms like Deutsch-Jose's demonstrating exponential speed-ups on contrived problems. Then, in 1994, Peter Shor discovers a quantum algorithm that can factor large integers in polynomial time exponentially faster than the best-known classical algorithms, striking directly at the security of widely used crypto systems like RSA, which rely on the practical difficulty of factoring. Shor's algorithm uses quantum Fourier transforms acting on superpositions of states to extract periodicity, illustrating the power of quantum parallelism and interference. Soon after, Love Grover devises a quantum search algorithm that offers a quadratic speedup for unstructured search, again using amplitude amplification. These breakthroughs catalyze a new wave of experimental efforts to build quantum hardware. Different platforms vie for primacy, trapped ions in electromagnetic fields manipulated with laser pulses, superconducting circuits whose quantized energy levels form artificial atoms, photons in optical fibers and integrated circuits, nuclear spins in molecules probed by NMR techniques, defects in solids like nitrogen vacancy centers in diamond. Each faces the challenge of decoherence, the process by which entanglement with uncontrolled degrees of freedom, phonons in a lattice, fluctuating electromagnetic fields, cosmic rays, rapidly destroys delicate superpositions, making qubits behave classically. Quantum error correction, developed in the mid-1990s by Shaw, Steen and others, offers a way out, encoding logical qubits into entangled states of many physical qubits, such that errors can be detected and corrected without measuring the encoded information directly. This requires subtle use of entanglement and redundancy, and demands high fidelities and low error rates, leading engineers and experimentalists into a regime where they must design and control quantum systems with exquisite precision, pushing the strange principles of quantum physics from thought experiments into technological realities. Alongside computation, quantum cryptography emerges as a practical application of quantum weirdness. Protocols like BB84, proposed by Bennett and Broussard in 1984, use the fact that measuring a quantum system in one basis disturbs its state in incompatible bases, making eavesdropping detectable. Two parties, Alice and Bob, can exchange qubits encoded in polarization states of photons. Any attempt by an eavesdropper, Eve, to intercept and measure these qubits will introduce errors that Alice and Bob can detect by comparing a subset of their data publicly. Growing experiments over optical fibers and even satellite links demonstrate quantum key distribution over ever longer distances, promising unconditionally secure communication based on the laws of physics rather than computational assumptions. Entanglement-based protocols, rooted in Eckert's 1991 proposal, tie security directly to the violation of Bell inequalities, weaving together foundational non-locality with practical encryption. If quantum information theory treats quantum states as carriers of computation and secret keys, another frontier regards them as elements of space-time itself. In attempts to merge quantum mechanics with general relativity, several strands of thought converge on the idea that entanglement and quantum correlations may underpin the geometry of space-time at the deepest level. In the anti-de Sitter conformal field theory, ADS CFT, correspondence, proposed by Juan Maldacena in 1997, a gravitational theory in a higher dimensional bulk space-time is mathematically equivalent to a quantum field theory without gravity living on its lower dimensional boundary. This holographic duality suggests that space-time geometry and phenomena like black holes can be encoded in the entanglement structure of the boundary quantum state, and that concepts from quantum error correction describe how local bulk physics emerges from non-local boundary degrees of freedom. Tensor network models such as Mira provide toy examples where entanglement patterns map naturally to emergent geometry, and the slogan "It from Qubit" captures the growing belief that quantum information is not just a tool for engineers, but a constituent of reality. Black holes, once purely theoretical solutions in Einstein's equations, become a crucible for quantum gravity when Hawking, in the mid-1970s, shows that quantum fields in curved spacetime lead black holes to emit thermal radiation, losing mass and eventually evaporating. This Hawking radiation appears featureless, characterized only by the black hole's macroscopic parameters like mass, charge, and angular momentum. If a black hole forms from a specific pure quantum state and evaporates completely into thermal radiation, the final state seems mixed, implying loss of information and violation of unitarity, a core principle of quantum mechanics. This black hole information paradox pits quantum theory against general relativity and has driven decades of research. Proposed resolutions include remnants, subtle correlations in Hawking radiation, or modifications to the semi-classical description. In holographic settings, especially ADS-CFT, evidence accumulates that information is not truly lost. The boundary quantum theory is unitary, and black hole evaporation corresponds to complex but ultimately reversible evolution. Recent ideas involving quantum extremal surfaces and replica wormholes connect the Page curve, which tracks entanglement entropy of Hawking radiation over time, to geometric quantities, intertwining quantum information, semi-classical gravity and geometry in unexpected ways. While theoretical physics reaches towards such dizzying heights, quantum phenomena continue to manifest in controlled laboratory systems at ever finer scales. Ultra-cold atomic gases, trapped in optical lattices formed by interfering laser beams, simulate condensed matter models with tunable parameters, allowing physicists to emulate Hubbard models, observe the superfluid Mott insulator transition, and explore topological phases with synthetic gauge fields. These systems realize Bose-Einstein condensates and degenerate Fermi gases with unprecedented control, letting researchers watch vortices in superfluids, test BCS-Beaky crossovers, and probe non-equilibrium dynamics in quench systems. Rydberg atoms with highly excited electrons far from the nucleus provide long-range interactions and giant dipole moments, enabling quantum simulators that can mimic spin models and even attempt rudimentary adiabatic optimizations. In mesoscopic systems, coherent transport of electrons through quantum dots and interference in Aharonov-Bohm rings demonstrate phase coherence of electronic wave functions over micron scales, while superconducting qubits, transmons, flux qubits, phase qubits become building blocks in devices cooled to millikelvin temperatures in dilution refrigerators, where microwave photons choreograph their interactions. Topological quantum computing, inspired by the fractional quantum Hall effect, and theoretical constructs like non-abelian anyons, proposes storing quantum information in global topological degrees of freedom that are intrinsically protected from local noise. Braiding non-abelian quasi-particles around each other in 2 dimensions implements quantum gates via their world-line topology, with computational operations encoded in paths rather than local manipulations, promising robustness against decoherence. Majorana zero modes, exotic quasi-particles that are their own antiparticles, are predicted to appear in certain superconducting hybrid structures, such as semiconductor nanowires with strong spin-orbit coupling proximatized by S-wave superconductors under magnetic fields. Experimental reports of signals consistent with Majorana modes have spurred intense efforts to confirm their existence and harness them, though debates about interpretations continue, and the dream of fault-tolerant topological qubits remains tantalizing but unfulfilled. All the while, decoherence theory provides a more precise account of how classicality emerges from quantum origins. Pioneered by Zurich and others, decoherence describes how a system's entanglement with its environment causes interference terms between components of a superposition to diminish rapidly when tracing over environmental degrees of freedom, making the reduced density matrix effectively diagonal in a certain preferred basis. In this view, there is no need for a fundamental collapse. Instead, coherence between macroscopically distinct branches becomes inaccessible, and observers, themselves quantum systems entangled with their surroundings, perceive a world of definite outcomes because their information is limited to one branch. Decoherence does not by itself solve the measurement problem. It explains why certain observables become effectively classical, but not why a unique outcome is experienced. Yet it knits together quantum theory with thermodynamics and statistical mechanics, invoking concepts like entropy and information flow to describe the transition from micro to macro. As the 21st century progresses, the strange world of quantum physics, once confined to the blackboards and chalk dust arguments of European institutes, becomes embedded in commercial devices and national strategies. Quantum sensors, exploiting squeezed states of light or entangled atomic ensembles, push precision measurements beyond classical limits, enabling more sensitive gravitational wave detectors, magnetometers that can read neural activity, and atomic clocks with stability precise enough to detect gravitational time dilation over centimeter height differences. Quantum random number generators, based on fundamentally unpredictable quantum processes like photon arrival times, feed cryptographic protocols with genuine randomness rather than algorithmically produced pseudo-random sequences. Governments around the world fund quantum initiatives, seeking quantum computers that could break codes or solve complex optimization problems, quantum networks that could distribute entanglement over cities and continents, and quantum materials that might revolutionize electronics and energy technologies. Yet beneath these ambitions, the core questions that haunted Planck in his Berlin office and Einstein in his Bern flat persist in altered guises. Why does nature, at its root, seem to be governed by amplitudes that interfere rather than by probabilities that simply add? How does the smooth, unitary evolution of the wave function reconcile with the discrete character of measurement outcomes? Is the randomness observed in quantum experiments truly fundamental, or does it emerge from deeper deterministic dynamics hidden from us by scale or principle? Are space and time emergent from some pre-geometric quantum substrate, with entanglement acting as the threads from which distances and causal structures are woven, or are they fundamental arenas within which quantum fields play? As experiments probe larger and more complex systems in superposition, massive molecules interfering in double-slit setups, mechanical oscillators cooled to their quantum ground states, entangled photons sent between satellites and ground stations, the boundary between the microscopic and macroscopic, once thought sharp, dissolves, revealing a continuum on which quantum rules hold sway as far as we can test. In laboratories lit by the cold glow of monitors and the soft buzz of vacuum pumps, graduate students adjust lasers whose coherence lengths stretch kilometers, align optical cavities where photons bounce tens of thousands of times before escaping, and monitor cryogenic stages where chips etched with niobium circuits host qubits that flip and entangle in nanoseconds. In these spaces, the bizarre phrases that once belonged exclusively to philosophical treatises, superposition of states, non-local correlations, vacuum fluctuations, zero-point energy, are translated into calibration numbers, error bars, and timing diagrams. The path from Planck's desperate act to here winds through wars, revolutions, conceptual schisms, and technological booms, but at each turn, nature has refused to retreat into classical simplicity. Instead, it has met each new probe with behaviors that demand the full machinery of quantum theory, from the discrete jumps in atomic spectra that first disturbed Bohr's sleep to the qubits whose fragile coherence now occupies the attention of engineers and theorists alike, and in the intricate superpositions flickering on those chips, in the entangled photons racing through optical fibers beneath our cities, the story that began with a misfit curve of blackbody radiation continues to unfold, drawing us ever deeper into a world where particles are not merely points, waves are not merely ripples, and reality itself seems to be written in a language of complex amplitudes and elusive certainties that challenge our intuitions even as they underwrite the technologies by which we listen, calculate, and, for a time, glimpse the hidden order behind the shimmering veil.